And before we start, just want to know whether you guys have a problem with your assignment 2, anything that you want to clarify. Ada apa-apa soalan ke untuk assignment 2? Any question for assignment 2? So all is okay? Nazir ada nak cakap something ke? Tu?
Tak ada, Doktor.
Okay. Alright. I see. So today we are going to continue from what we have started. I think last week we have gone through potential dynamic polarization, and weight loss. So just a quick recap before we continue the other parts. For weight loss measurement, as I said, this method is basically a very simple and a cheap process. And another thing that you have to put in your mind is that for weight loss method, this process is basically a naturally occurring process where you just put the metals in the environment and then you leave it at certain time. And after that, you weigh the mass before and after. Okay. So this method actually have some advantages and disadvantages. Advantages, of course, it can be applied to various types of environment. But the major disadvantages is because it is a time-consuming process. It's not compared to other electrochemical techniques, which is mostly induced current techniques. Weight loss measurement, basically a time-consuming process. It takes some time, and it have a higher percent of error as compared to other process, because you are not going to get the same value, and the value deviation is basically quite huge if you compare like day or maybe the other times that you do the test. You are not going to get the same results. Outcome from weight loss measurement, you can actually calculate corrosion rate. Basically, we have looked at this formula from chapter 3, if I'm not mistaken. And we can also calculate the inhibition efficiency based on the mass loss. So in case of, if you add corrosion inhibitors at the different concentration, you can actually study what will be the inhibition efficiency. The higher the inhibition efficiency is, meaning that the process of corrosion is less likely to occur. It's going to be difficult. And we have also looked through potential dynamic polarization methods. And the name itself, polarization, means that we studied the behavior of a current at the different potential values, at the different over potential values. From the stable state or from the equilibrium potential, we polarize it more positively or more anodically to more negative or more cathodically. So the behavior of current that we will get at the end will actually give us some information whether the materials actually experience passivity, limited current density, or other things. And we also have looked at active-passive transition, okay, where passive actually, or passivation actually happen when you have the formation of very stable metal oxide, okay, on the surface of the metals. And I think if we proceed measuring the potential or measuring the current at higher potential, you can actually notice that a failure of passive layer can happen, and this actually leads to the formation of pitting corrosion.
Sir, could you accept jihad?
Jihad. Sure, no problem.
Yeah, thank you so much.
Okay, and for the outcome, basically you will get a Tefl plot, so-called Tefl plot. We have seen Tefl plot in chapter 4 in polarization part, and this actually will give us a new dimension. It will give us another values or parameters. For example, potential of corrosion, E core, the corrosion current density, I core, beta anodic, beta cathodic, which is the slope of anodic and cathodic potential, okay, or linear plot. And others will be corrosion rate. This will be secondary. After you get the I core, you can actually calculate the corrosion rate based on the formula. Okay? Corrosion rate in MPY is equal to 0.13 multiplied with I core in microamperes multiplied with equivalent weight over density. Some examples, results that you will get from potential dynamic polarization methods and how to double check your values for corrosion rate from the software, and also if you calculate it manually. Okay. And the unit conversion for MPY to MMPY, as I said, you need to multiply it with a factor 0.0254, and if you multiply with this factor, you can actually get the conversion to millimils per year. We also look at the effect of inhibitors in terms of potential dynamic polarization. You will see that when you add inhibitors, it will actually form a curve that is lower than blank, or lower than with the presence with the absence of inhibitors. So this actually indicate that when you add the inhibitor, it will produce lower current. Lower current means it will produce a lower corrosion rate with a higher inhibition efficiency. Okay. Right. So another thing that I would like to stress on, if you have this kind of a discussion, we look at not only the lower curve, okay, but also the shifting of E core, and also the difference of beta A and also beta C values. This actually will indicate the types of inhibition, whether it will be cathodic inhibitors, anodic inhibitors, mixed type with predominant anodic, or mixed type with predominant cathodic. Right. So this kind of examples mostly been asked during exam. So I hope that you are able to understand the phenomenon of inhibition, as well as to predict the types of inhibition, whether it will be cathodic, anodic, mixed type with predominant anodic or predominant cathodic. And the last part that we have looked last week was pitting corrosion, measurement of pitting corrosion by means of cyclic polarization. So with potential dynamic polarization, if you make it in reverse, okay, if you actually measure until certain potential and then you make it reverse, you can actually determine other information, for example, like pitting potential, repassivation potential, IP, or pitting current density, and others. So this actually one of the useful tools to measure pitting corrosion. So the profile of TEFL plot that you will get in the end is not only a reverse TEFL, but also a production of hysteresis loop. As I said, if you have a bigger area of hysteresis loop, it means that you have massive or a lot of heat. Okay. So this give you some indication how severe the corrosion process or how severe the pitting process is, right? Okay, so with the addition of corrosion inhibitor, you can also see that the hysteresis loop is lower or smaller. Then this actually indicate that you have a lower pitting or low pitting. Other than that, you look at the current density values, whether it's going to be high or low, the shifting of eco and others. So today we are going to look at what will be the requirements for electrochemical process. Of course, this is just a recap from probably chapter 1, the requirements for electrochemical process, you need working electrodes. As I said, working electrode will be the studied electrode. This is actually important if you are studying a different types of metals or alloy. You will put these metals of alloy to be working electrodes. Reference electrode in turn is basically to measure the potential produced from your working electrodes. So you can use different types of reference electrode ranging from silver chloride, standard hydrogen electrodes, and others. Other things that I would like to introduce over here is actually known as Laging probe or Laging capillary. Laging is actually the name of a person. Okay. What is actually the function of Laging capillary? Okay. So if you notice over here, okay, you will have a working electrode and the counter electrodes or auxiliary electrode being placed. Okay. And as I said, electrochemical process, it will depend on how close the working electrode to a reference electrode interface. Okay. So if you want to get a very good electrochemical data, you have to make sure that your working electrode being placed as near as you can with the reference electrode. Because the function of reference electrode is basically to measure the potential. But when you look at this diagram, you will see that the reference electrode being placed to another container and connected with a solution bridge. And this actually bridge is known as Laging capillary. Okay. Laging capillary also function as like a salt bridge to complete the cell. But why the reference electrode being put, okay, at the other container is basically um, to have less interference. Okay. When you have less interference, it means that the measurement is not being influenced by other types of species that presents in the your electrolyte, maybe other effects. But if you notice over here, the Laging capillary actually will make our objective become achievable because the Laging capillary will be placed as near to the working electrode surface as you can. So in fact, the main function of Laging capillary is to reduce IR drop. Okay, to reduce IR drop. If you still remember, I have actually explained what does it mean by IR drop in the previous chapter. So IR is actually current resistant drop. If you have anything, like for example, a coating or other types of impurity, passive layer or what, that can actually give an increase to higher resistance or I think difficulties in electrochemical measurement, then the position of reference electrode will need to be put as close to the working electrode. Okay, so that is why the Laging capillary has been placed near to the working electrode, and in fact, the distance between the working electrode to the Laging capillary must be equal to the diameter of the capillary. Okay. So the distance A should be like almost equal to the distance of the or the diameter of the capillary. So this actually will allow a better charge transfer process. Okay. Allow a better charge transfer process. And at the end, you will get a better electrochemical data. Okay, all right. Other things will be the requirement of counter electrode to measure current solution as the working electrodes. Okay, working electrolytes. And other thing will be reflecting on the mass transport, which actually controls the diffusion, migration, and also the convection process in the interface process. Right. So we are moving on to the next process or methods, which is known as linear polarization resistance. Okay. In STM, it is known as SMG59. Okay. And for linear polarization resistance, sorry, in chapter 4, we have looked at what will be the response of current to potential. You'll get something like this, okay? At the current 0, this is where your E core is. And at the higher potential, this is where the neta A or the anodic overpotential occurs, and at the lower potential value, this is where your neta C or cathodic overpotential occurs. The slope for here is actually equals to beta A. The slope for here is actually equals to beta C. Okay, and in fact, the slope in the middle is actually equals to RP, resistance of polarization. This is actually the essential of linear polarization process, where you will get polarization resistance or resistant polarization, RP. So RP can be obtained, okay, as the slope for changes of potential over the changes of current. So close to equal, the current versus voltage curve approximates a straight line. The slope of this line has a unit of resistance. The slope is therefore called polarization resistance. An RP value can be combined with an estimation of beta coefficient to yield an estimate of corrosion current. Okay. So you can actually calculate what will be the I core value, because here you cannot get simply the I core value, because as I said, at current 0, this is where you get your E core, this is where you get your beta A, beta C, the slopes. And when you calculate the slopes of the difference of, the difference of potential versus over difference of current, you will get RP. Okay, you can eventually calculate I core from a formula. Okay, RP is equals to beta A multiplied with beta C over 2.303 times I core times beta A plus beta C. This is actually a formula to calculate RP with a correlation of I core. So in case of you already get RP, since RP, you know that it is a difference of potential over difference of current. Okay, then you can calculate I core beta A plus C over 2.303 times I core times RP, not I core times RP times beta A plus beta C. All right. And another advantage of doing linear polarization resistance is that if you remember for potential dynamic polarization, PD methods, okay, the overpotential range is actually plus minus 250 millivolts from equilibrium potential, EQ or EOCP. But for linear polarization resistance, okay, the range will be plus minus 20 millivolts from equilibrium potential. Why? Because this is actually to ensure linear line Okay, because at the end you want to calculate the RP value. Okay, so you need a linear line at a very small range. Okay, so if you actually scan at the higher potential values, then you are not going to get a very nice linear. Maybe it's already bigger, then you cannot actually calculate the best slopes, right? So this process or this method is known to be a fast process as compared to potential dynamic polarization. Faster. Maybe it takes only 1 or 2 minutes to complete as compared to potential dynamic polarization. For potential dynamic polarization, since the scan is quite huge, plus minus 250, so maybe altogether you have like in one range, 500 millivolts of potential need to be scanned, then it will be time consuming as well. Okay, slightly time consuming. So, any questions so far for linear polarization resistance? Ada soalan? Right. The scanning of potential about 20 millivolt cathodic to 20 millivolt of anodic to the corrosion potential produce a linear polarization, also known as polarization resistance scan. The slope of the resulting approximately straight line is proportional to the corrosion rate. Linear polarization technique is useful for determining the effect of corrosion rate of a number of possible corrosion inhibitors added at different concentrations. Information can be obtained from these techniques relatively quickly to allow decision to be made on what to include in more time-consuming and complicated laboratory or field tests. As I said, since the range of potential or the over potential is quite small, then the process is known to be a fast process, sorry. Right? So this is basically what we are talking just now. The design of linear polarization plot or linear plot that you get. This is actually plotted potential against current. You can actually plot current versus potential. You will get the same shape basically. So this is actually the region that you want. Okay, the one that have a very linear part, where plus minus 20 millivolt. And when you calculate the slope, you will get the resistance. Okay. So I guess the explanation of polarization have been taught in chapter 4. How you can actually get polarization is basically a measure of a different range of potential, a measurement of current, okay, at different over potential values, anodically or cathodically. And this is also what you have seen in chapter 4 as well. The relation of over potential to beta A, or the slopes of TEFL, beta A and also beta C. Right. So this is basically what I have taught you just now. How you can actually calculate I core, okay, from RP values. So from this TEFL slope equation, okay, you can actually substitute it into equation 7 and 8. Equation 7 and 8 is basically a term that relates the O potential with the TEFL slopes. So you can actually substitute these things together, and then you will get another formula that is actually known to be RP equals beta A multiplied with beta C over 2.303 multiplied with I core multiplied with beta A plus beta C. So in case of you want to calculate I core, you just substitute the position. Okay. Then you will get this formula. So at the end, the essential part from linear polarization methods as compared to PD, linear polarization will give additional information or values of RP, where RP you cannot get it from PD measurement directly. And for linear polarization, you will get RP first, then only you can calculate your I core based on a formula. So I believe maybe later on we will decide on our practical session. So you will actually calculate the I core values later on when you have obtained your data, linear polarization data. So you can double check whether you will get the same I core value from PD and also from LPI. Okay, so a similar explanation as what I've told you just now for linear polarization resistant methods was like scan at the lower potential range, okay, plus minus 20 or 25 millivolts from E-core. Okay. With a lower scanning rate may be around 0.1, 0.25 or 0.5 millivolt over second. Then this actually will take you less than even 5 minutes or less than 10 minutes. Normally for potential dynamic polarization methods, if you choose like 0.1, 0.5 or 1 millivolt over seconds, normally will take like around 7 minutes up to 10 minutes. But if you do linear polarization methods, it will take like less than 5 minutes, maybe like 2 minutes, I guess, to complete the measurement. Right. So some examples, just to show you how you can actually calculate this, what you will obtain from linear polarization methods. You will get a value of RP, you'll get beta A, beta C, and the others will be the factors that you already know, equivalent weight of a steel, density of a steel. Okay. So by applying the formula, okay, you can actually calculate I core value. So RP is already known, 3.57. So you just multiply with the beta values. And things that you need to remember over here is that beta C value, okay? So we're not going to address beta C as negative. It will be always positive if you want to use this formula, okay? So if you recall back the formula that you will get for mixed potential, log I naught is equals to EA minus EC, then plus beta A log I A, and then what? Minus beta A log I naught or what? And then you will have like over beta A plus beta C. So this actually you need to use negative symbol, except that this one you will use a positive value, or you change the potential value to anodic. Okay, but for this one, okay, the beta C value is always going to be positive, because if you notice the linear polarization plot, okay, it is always positive. Okay, you get a positive linear for anodic, you get a positive linear also for cathodic. Okay. So negative beta C is only happen when you have Tafel plot, because Tafel plot is basically plotted log current density versus potential. Then you will get something like this. Then this actually the beta C, and D is actually beta A. So that is actually the difference. Any questions so far? Anything that you would like to ask? Or not clear? Is it okay to everyone?
It's okay, Doctor.
So if you actually substitute all the values together, okay, you will get the I core value as follows. So the I core values will be reported as it is. It will be in amperes, not in microamperes or watt. Okay. And finally, once you get the I core values, you can substitute in this formula to calculate corrosion rate. So at the end, you have like also corrosion rate values, which can be calculated from linear polarization methods. Right. So what about the effect of corrosion inhibitors when you do linear polarization methods? The trend is not going to be the same as if you do potential dynamic polarization. Remember, in potential dynamic polarization, okay, you will measure current density. Meanwhile, for linear polarization methods, you will calculate or you will measure polarization resistance. You will get polarization resistance. So what would be the logic if you add corrosion inhibitor? Adding corrosion inhibitor will give certain effects. The first one, you will get a trend where a lower current density will be produced. So lower current actually will produce higher resistance polarization. So that is why if you notice over here, when you have a different concentration of inhibitor added on, it is actually increasing the concentration of corrosion inhibitor, CI. You will notice that the RP value is also increased. Okay. So when you have an increase of RP, is also mentioning that you have an increase in inhibition efficiency and also a decrease in corrosion rate. Right. So how you can actually calculate inhibition efficiency based on linear polarization or polarization resistant value? This is actually the formula. Okay. Inhibition efficiency for LPI method is calculated as polarization resistant with the presence of inhibitor minus blank, RP of blank, divided with RP of inhibitor, multiplied with 100. So we take one example, probably at concentration of 1 times 10 power of, 1 times 10 power of minus 2. So the IE values can be calculated as 91, okay, minus with 30, okay, because 30 is basically without the presence of inhibitor, divided by 91 multiplied with 100. So you'll get a value of 97%. So the rest should follow the same thing. Okay. This is basically the observation that you will get if you do linear polarization measurement and if you want to calculate inhibition efficiency based on linear polarization data. Okay, so the other difference for PD, okay, the potential range is plus minus 250 millivolts. Meanwhile, for linear polarization, it will be just plus minus 20 millivolt. Okay. What will be the other difference? Okay. So you cannot get P directly. Maybe you have to calculate. Meanwhile, for LPR, you cannot get I core. You have to calculate from a formula, then only you will get. The similarity, okay? The clear similarity is because this both process is actually DC process, a direct current, which means the process is destructive. Destructive measurement. Okay? Anything? Yes.
Can I get inhibitor efficiency by eye corrosion?
By?
By eye corrosion?
You can, yes, you can. You can get you can calculate the I core value. Yeah. For example, RP from here you convert into I core using the formula that we have see just now. Okay, I core equals to beta A, beta C, 1.303. If you actually calculate one by one, the I core for individual, you can still calculate the inhibition efficiency using I core. Okay, values maybe not going to be the same. Okay, meaning that the values of I core, but the trend will be the same. Okay, but in case of you want to calculate I core, IE directly from RP, you can use this formula without actually converting first to I core, then only you calculate the IE. Okay?
Okay, thank you.
Any other question that you would like to ask? Anything? Right, we are moving on to the other parts of electrochemical measurement for corrosion. This part is considered to be one of the longest part in this chapter because, of course, for EIS, it will take like some time to get the students to understand the phenomenon and the process. Okay, so the process or the methods that we can do in order to measure corrosion is basically by electrochemical impedance spectroscopy, EIS. This method is very known to be a complicated process, very hard to understand, okay? But it is very unique as compared to the other process that we have learned, weight loss, potential dynamic polarization, and also linear polarization resistance. Okay. The essential of electrochemical impedance process is basically this process acquire EC methods or AC current, alternating current, in comparison with other methods like potential dynamic polarization, linear polarization resistance, electrochemical noise. All that is actually using direct current. For EIS, you will use alternating current. So that is why it is named as impedance. Why? Alternating currents means that the current is actually flow in and flow out. It is not directly flow. So when you do EIS, and when the process is basically use alternating current, the process itself is known to be non-destructive. Oh, right. Non-destructive. Non-destructive means that the sample or the working electrode that you use, you still can use it for another purpose. It didn't actually damage the sample. So that is why a good practice when you do a sequence, electrochemical process at one time, you can actually do OCP first, okay, followed by EIS, and followed by potential dynamic polarization. If you want to get like all three data from one time experiment, because OCT actually you didn't apply current, no current is being applied. Okay. EIS, it is non-destructive process. And lastly, PD will be the destructive. So if you do this kind of sequence, you can get three data at one time for one type of sample or one type of running. Okay, right. So what is impedance? In DC theory, in direct current theory, okay, for Ohm's law, you will get potential is equals to current multiplied with resistance. In AC system, the Ohm's law will be E is equals to I Z. Z is actually known to be impedance. Okay? But what makes the difference between R from DC and Z from AC? In direct current, okay, in direct current, only resistor produce this effect. Okay, so the resistance that you will get actually will give a resistor. However, in alternation current or alternating current, two elements that you will get at the end, capacitor and also inductors. Okay, all right. So as I mentioned earlier, in DC system, the Ohm's law has been defined as E is equal to IR, where E is actually the potential, I is actually the current, and R is actually the resistance in ohms. Okay. A resistor is the only element that impedes the flow of current. So the flow of current, okay, can be slowed down, okay, with the effect of resistor if you are doing DC system. But in AC system, the flow of current can be slowed down due to the presence of capacitor and also inductors. That is why you will get the Ohm's representation for AC system. E is equal to IZ. Okay. Z is defined as impedance, the AC equivalent of resistance. So basically Z and R is almost the same. The unit is actually in ohms. It's like resistance, but the term cannot be similar because one is actually from DC system, the other one is actually from AC system. So you have to actually differentiate the two, because as I said, the factors that influencing the flow of electrons in direct current system is basically with the presence of resistor. But in DC system, the factors that influence the flow of electron is basically with the presence of capacitor and inductors created from the alternating current process. Principles of EIS measurement. Electrochemical impedance is usually measured by applying alternating current potential to an electrochemical cell and measuring the current through the cell. EIS technique, where a small amplitude signals, usually a voltage between 5 to 50 millivolts, is applied to a specimen over a range of frequency. So this method is known to be potentiostatic. Why it is called as potentiostatic? Remember, potentiostatic means you actually use a constant or a standard potential value, only one value, a sole value. when you do a measurement. So between 5 to 50, you will actually use only one potential values, okay? Amplitude signals, okay, with a voltage values around that, and then it is actually measured at the range of frequency. So for impedance, the main parameters will be range of frequencies. If you remember, for PD and also LPR methods, the main parameters will be the range of potential, plus minus 250 for PD, plus minus 20 for LPR. But for EIS, you actually use frequency, not potential. Potential, you just keep it constant. Okay? You measure the current with a function of frequency. And what would be the range of frequency recommended? This one. Okay. Normally for EIS, you will do the measurement at the higher frequency to a lower frequency, 1,000 or 100,000 hertz to the slowest, maybe 0.1 or 0.01. Like this one, it says 0.001. Okay. You can actually use even lower, 0.001, but the range will be too big and the process will be time consuming to get the data. Okay, so for me, normally I will use this value or range whenever I do electrochemical impedance measurement, 100,000 to 0.01 hertz. And this one is normally taking almost like 30 minutes or 40 minutes to get one data. Since the most relevant information regarding the corrosion reactions over this range, the EIS instrumentation records the real and also imaginary components of impedance response. So that is why you will get Z prime and Z2 prime. So when you do EIS, you will get a response. Okay. When you do PD, you will get a response of current. When you do LPR, you also get a response of current at different potential. But for EIS, at different frequency, you will get a response of Z real and also Z imaginary. Okay, so why is actually Z prime and Z2 prime? Real impedance, and Z2 prime is basically imaginary impedance. Okay, I will explain to you how you will get real impedance and also imaginary impedance. This is basically the instrumentation setup. Same as other methods, you will have electrochemical cell, you have reference electrode, you have working electrode, and also counter or auxiliary electrodes. Connected to potentiostat, okay? Here it means that you use potentiostatic. Okay, you use basically a constant values of potential. Then the information that you will get is basically a change of current, okay? And slightly maybe a change of potential as well. Okay? So the data that we will obtain will be analyzed, and then it will goes into the computer, and the computer will basically give you a plot. Okay? So the plot that you will basically get from EIS method is known to be border plot, and also Nyquist plot. Border, B-O-D-E, and Nyquist, N-Y-Q-U-I-S-T. Okay. All right. So how actually you get like imaginary and also real impedance? So this is actually the things. Imagine that you have the cell. Oh, sorry, cell is over here. Okay, and this is actually your supply. The supply is actually giving you a potential static. This is actually a potential static potential values. When you do the measurement, it will give a response of current. So since I said to you that the process itself undergoes at the AC system, alternating current at different frequency. So when you put in your mind, if you learn physics, the response of frequency will be as what? Anyone knows? What would be the response of frequency? The response of frequency is always a wave like response. It's like a wave. So that is why over here you have like variable frequency sinusoidal wave generator. Okay? Because you're measuring the EIS system in a different set of frequency range. Then you have a different response. Different value will give you different response. So not sure whether you still remember in physics, you have okay, you have a different response that is known to be as sine theta and also cos theta response. So what will be this sine theta and cos theta? This is actually the response of wave that you will get. As I said, different current value will produce a different response. And if the response is actually forming like a sine theta waveform, this actually will result an imaginary theta. Okay, so 1 point of current, sine, so you will get imaginary. In contrast, if the response is basically in the cos theta mode, you will get real impedance. Okay. So at the end, it doesn't mean that for one sample, you will get only one imaginary or one real values of impedance. You can get multiple because the range is basically at the bigger range of frequency. So maybe at one point you have like um, both real and also imaginary. So all this being recorded, and at the end it will produce a plot. Okay? So the plot that you will get, as I said, is basically on border plot and also Nyquist plot. And this one is actually an example of a Nyquist plot. Okay, where you have like Z2 prime versus Z prime, imaginary versus real, forms like a semicircle. Okay, right. What would be the importance of EIS? Why people use EIS as part of these methods in order to measure corrosion of metal? The main reason is because EIS provide interfacial information, which this information cannot be seen in PD and also LPR. For example, if you are studying metals that is known to be unknown, you don't know whether the metal is been coated, you don't know whether the metal have a different layer, you don't know whether the metal have a different composition or what. So if you do PD, it's just you give you a TEFL only to see the anodic and also cathodic reaction. But for EIS, it will give you some indication, because the importance of EIS is because it will give a resistance, so-called impedance, okay, value. So if you see that there's a formation of multiple resistance, so you know that, okay, you have a multi-layer, okay, of product that forms on your electrodes. Maybe if you have a coating material, you have like a porous resistor and something like that, then you know that, okay, for unknown sample or for this kind of things, I actually have a coating layer, a passive layer, or other things. An important part of EIS analysis is to create equivalent circuit. Data that you will get in EIS modulus Z versus frequency, and also phase angle or pi, pi or theta versus frequency. We have not come to this part yet, but I guess maybe I just like show to you what will the result look like when you do a simple corrosion process of steel in water or in electrolyte. For border plot, the plot is basically modulus Z. Modulus Z is actually the sum of real plus imaginary. Z prime plus Z2 prime. This is actually equals to modulus Z. Frequency is just still frequency, and phase angle is actually the degree of rotation. So we will see what does it mean by rotation after this. So border plot, actually you have like two curves at one time. You have like a resistant curve for modulus Z versus frequency, this one, like a step, okay? A step plot. Meanwhile, for phase angle, you will get like a peak or like a loop, one peak. So what does this indicate? This actually gives you some indication how much electrical component that you will have. So this electrical component is basically to relate with the interface information. Meanwhile, for Niki's plot, as I said, it is actually obtained from the same data. It's just the way how it is interpreted is different. Niki's plot is basically a plot between Z imaginary versus Z real. Then you will get like a semicircle like this. Okay. So once you get the data, it is actually important to fit your data with a model. It is actually the same thing when you do linear, or I guess maybe you have learned in 507 adsorption isotherm. If you fit to a model, it actually explains to you what will be the mechanism. For adsorption, you learn about Langmuir, you learn about Fromkin, you learn about Friedrich model, you learn about Temkin model. So if the data, your data is actually fit to this model, then it's actually correlate with the hypothesis. Like Langmuir, it says monolayer. If Temkin, it says chemical adsorption, chemisorption. So it's also the same thing for EIS. If it is fitted to a circuit model, okay, then it actually explains the types of interface mechanism that happens between your working electrode and also reference electrode. Right. And to create equivalent circuit, you also need to know what will be the component. Okay. the electrical component that you should have in the data. So as I said, we didn't actually do these things electrically, but the mechanism, the interface mechanism actually mimics the electrical mechanism. So that is why it is need to be fit with electrical circuit using resistor and also capacitor in series and also in parallel. The physical behavior of the corrosion system can be simulated and quantified with the circuit to gain insight into the important process of the corrosion system. In electrochemical cell, a slow electrokinetic, slow proceeding chemical reaction and diffusion can all impede the electron flow and can be considered analogs, okay, analogs to the resistor, capacitor, and inductors that impede the flow of electron in the AC circuit. All right. So basically, when you do the measurement for maybe a simple metal in electrolyte, you will get a border plot like this. Okay. There's a trick actually to know how or what will be the electrical component that you will have in your system based on your border plot or based on the case plot. I guess maybe you will get to know this in detail after this. So as I said, why the equivalent circuit is important in order to fit with your data, because the double layer process that you learn in chapter 3, okay, the double layer process that you learn actually will give a mimic to electrical circuit design. So imagine that when you have learned so far about the interface, you have your electrodes or working electrodes. And this is actually where your reference electron will be placed. All process, the interface process is occur between these two electrodes working to reference electrode. Migration, diffusion all occurs over here. It will be captured. And for EIS, the important is we want to know what would be the mechanism, what would be the diffusion, what would be the charge transfer process that happens here, that we can actually relate it to the process. Okay. So as I said, if you have a metal, your metal will be oxidized. It will form positive charge. And what happens next? Migration process will occur first, where you have an electrostatic formation. Anion is basically attracted due to electrostatic. So this process is known to be migration. You know about this, okay? And this actually happens where? Anyone still remember? This actually happens in inner Helmholtz plane. And you have an outer Helmholtz plane or the bulk electrolyte. This is the region where the next process, the diffusion, because this will create like a Helmholtz double layer. Okay. And as another effect, you will have like a diffusion effect due to the concentration gradient. You have like more concentration of anions over here. That creates a so-called diffusion. Negatively charged species have been like covered all the way. Now, positively charged species will be diffused to go near to the So this actually will create so-called diffusion effects. Okay, right. So what will be the relation between this process with the one that we want to study with EIS and the correlation with electrochemical equivalent circuit? As I said earlier, so since you have the attraction of anions on the surface of the electrode, this will create a so-called double layer. And double layer you have learned in chapter 3. You have like three, you have like Helmholtz, you have like Goy-Chapman, and the combination of these two will actually become Stern effect. Right? So when you have a double layer, this coincidentally will create a capacitor. We assume that it will form like some capacitor on the surface, and the process of charge transfer can be assumed to form a resistor. So capacitor is basically formed due to double layer, and the charge transfer process, okay, charge transfer process will actually form a resistor effect. So that is why if you look at this explanation, this is your electrodes, and you have a migration and the attachment of the species on the surface. So this actually will create a capacitor. Okay? So this is actually a capacitor, okay? And this is actually a resistor, charge transfer resistor, RP or RCT. And you also have another resistor that is actually from the electrolyte, okay? Known to be RS, or resistance of solution. So this is basically a simple model to explain the concept of corrosion of metal in electrolyte. A very simple one, without any coating or without anything. Okay? And this model is known to be Randall's circuit design. Okay? So this N is WE, and this N is actually your reference electrode. Okay. So the information that you will get when you do the EIS, for this kind of system, you will get RP or RCT. Mostly we call it as RCT, but it's actually equals to RP as well. Polarization resistance or charge transfer resistance. CDL is actually double layer capacitance, and RS or RE is actually resistance of solution or electrolyte resistance. Okay. Any questions so far? Anything? Anything that you are not clear as is so far?
Doctor, there is only one capacitor here.
Yes, it's only one capacitor because you only have one double layer. But in case of later on, I mean, along the way when you learn this part, when you have a coating, for example, you have a layer of coating, then it will create another layer that we call it as coating capacitance or whatnot. But over here, right now, you only see one type of capacitance produced.
Yeah, because only one, I have one layer.
Yes, only one double
Okay,
layer
thank you, Doctor.
form.
Yeah, one double layer, yes, one.
Okay.
Okay.
All right. Although the linear polarization technique is valuable for bare metal in many situations, it is deficient for metals that are coated with electrically insulating materials such as paint or bare metals when the electrolyte is not very conductive. EIF solved this problem. So this actually what I tell you earlier on. When you do polarization methods, PD or LPR, you can see the oxidation process, reduction process, pitting and whatnot. But if you have a coating sample, okay, coated sample, normally EIS will be useful if you have a coating sample, coated sample, electroplating or sample that been applied with paint or whatnot. So if you don't know, I mean, like you see that it's transparent, maybe without any color or what, you would assume that, oh, this is just a normal metal, but instead it have a coating layer. So with PD, it cannot solve because it's just giving you a TEFL. But with EIS, it will give you an other information. It will give you a different shape that actually indicates that how many resistance that you have, how many capacitance that you will have. Okay? Right. So the equivalent circuit for a corroding metals, okay, you will have a double layer and also you will have charge transfer. So this is actually to relate the AC and also DC behavior. The low frequency where the double layer is high. Okay? So the current through RS or electrolyte or solution resistant and RF, which is the paradigm resistance, then it will actually follow DC behavior. In higher frequency, okay, where the double layer is low, then the current will go through the double layer and this actually will give rise to the effect of AC. All right. So probably you might thinking, where is actually the low frequency and where is actually the high frequency values. So if you recall back these slides that I've told you, you have a border plot. Imagine that if I make this into half and this I make it into half. This one is actually at high frequency and this is actually at low frequency. If you notice at the lower frequency, you have one resistor. So how to indicate actually from border plot, if you have a straight line, I mean a flat line like this. Okay? If you have a flat line, it means that you have a resistor. So over here, I have like two flat lines. Then means that I have two resistors. Okay. Another thing is if I have a slope. Okay? One slope actually means that you have one capacitor. Or from the phase angle peaks, you have seen maybe only one loop or one peak. So meaning that you have one capacitor. Okay. So over here at the lower frequency, this is where your C values, and at the high frequency, this is where your RS or solution resistant values. And what about nickel? You still have like make it into half. So from the origin to the first point, okay, so this will be your RS, resistance of solution. The diameter of the semicircle is actually equals to RCT. Okay, so if you look over here, from 0 to origin, you have RS. So where does, at which frequency that you think this happened? Low or high frequency? Anyone can guess? Actually, you can relate with the border plot. Diana, Channel?
High frequency.
Sorry?
High frequency?
Yes, correct. High frequency. And this is actually low frequency. So this is actually what it means. The low frequency, okay, CDL is high, then you have like a current through resistor. And then if we look at the double layer phenomenon as this, so which one do you think that the region of high frequency and low frequency? Maybe I should use a different color. Near to the electrode, this IHP region, right? Inner Helmholtz phase. So this one actually at the low frequency or at the high frequency?
At the low frequency.
Why at the low frequency, Mahdi?
Because
Because what?
well, it's not inside the solution.
Because
The concentration.
if you notice over here, I told you, you will get RCT, okay? The RCT value you will get at the region near to the electrode. Okay, so this is actually at low frequency. And OHP is actually at high frequency. Region where it is near to the bulk electrolyte. So back to this one. Low frequency means that this is actually at the region of IHP, and at the high frequency, this is actually at the region of OHP. And this one is the same thing, OHP, and this one is IHP. All right? Okay. So I don't want to confuse you too much, just to get you to understand how you can relate the double layer that you have learned in the previous chapter with impedance. Because as I said, impedance, the essential of impedance is basically to understand the interface mechanism that happens between your working electrodes and the reference electrode. So what types of mechanism? Okay, the mechanism that relates with the migration, diffusion, and whatsoever. But impedance is actually important if you have unknown sample or coated sample, because you don't know whether the sample is actually coated or what. Maybe it has some passive layer or some other layers that is not seen. Then if you do PD or LPR, this information cannot be discovered. Only with impedance that you can get the information. Okay, right. So in EIS concept, earlier on, I've told you that in the process of getting the data or getting the values of EIS, you will actually use a constant potential values, okay? And then you will use AC system, you will acquire amplitude of alternating current, then the response is actually in a wave form because it's measured in frequency. So if you look back in the border plot, as I said, border plot, you have two y-axis. You have like model z, and you have phase angle or pi. Okay, phase angle. Phase angle is basically the angle of rotation. So rotation what? Okay, so rotation of the frequencies. Okay, so this is actually the things that we are saying just now. So EIS is usually measured by applying AC potential to an electrochemical cell and measuring the current through the cell. Suppose that we apply a sinusoidal potential excitation. The response to this potential is an AC current system or signals containing excitation frequency and its harmonics. Okay, harmonics means that the waveform, harmonics. This current signal can be analyzed as a sum of sinusoidal function. Okay, I believe for this explanation, and probably this one or two slides regarding on excitation or rotation, uh, is just for your information. You don't have to like really understand it or memorize it because it's more physical, it's more electrical, which I'm sure chemistry students have a difficult time of understanding this. I mean, in fact, like me myself, I have also a difficulties on understanding the things earlier, but now because I've seen the process, I've seen like the data how it looks like, then I can actually relate the process. As I said to you earlier, the response of frequency would be like a waveform like this. You have like a response of cos, you have a response of sine. So if you still remember, you can actually get theta or the rotation. Theta is actually the angle, okay, from the difference of one peak to another peak. Okay, so this is actually the rotation. You're just assuming that when the signals is actually being recorded, okay, it has a different amplitude and it will give a different theta value, okay, because of different excitation signal. In a linear system, the response signal is shifted in phase and has a different amplitude. As I said, you will have a different response or signals depending on what will be the current value at that time and what will be the current value that you measure at the different frequency values. Okay? So it will result a different waveform or a different response to signal, which actually indicates that you have a different theta value. So for the expression of analogs to Ohm's law, you will get this one. I guess, like I said, this one is something that you didn't have to really understand entirely, but we know that to relate the impedance with the Ohm's law is the same as R is equals to a difference of potential over difference of current. So this is actually the difference. But the difference that we are looking at now is not the difference of potential or current, but the difference of the amplitude signals or the excitation signals, okay, of current and also at the potential. If we plot the applied sinusoidal signals on the x-axis, it will actually give us a plot known as Lissajous figures. So Lissajous figure is a mathematical figures that actually relate the response of the signal to the applied signals. So sometimes when you do a measurement of impedance, you will see that it will form like an oblong shape response. So this is actually a current to potential response in signal, in wave signals, known to be Lissajous figures. Just to relate, it will actually give you an information, as I said earlier, imaginary part and also real part. Imaginary part, if you have a so-called like a cos theta response and real part or real impedance when you have a sine theta response or waveform pattern. Right. So the Nyquist plot with impedance vector, okay. Nyquist plot, as I said, is one of the plot that you will get when you do impedance. So as I said earlier, how you can actually get Nyquist plot. Okay, Nyquist, or some people they call it as cold plot. It is actually plotted between Z2 prime to Z prime, imaginary to real. Imagine that you get a semicircle like this. As I said, from the origin to the first point is actually your RS. The diameter is actually equals to the RCT value. And from the first point to the midpoint, okay, this is actually your maximum frequency, F max. Okay. And the vector between RS to the maximum frequency you have angle over here, theta. So this is actually your phase angle. On the Niki's plot, the impedance can represent as a vector of a length modulus z. The angle between this vector and the x-axis is equal to pi. Niki's plot have one major shortcomings. When you look at any data point, you cannot tell what frequencies was used to record the point. When you look at Niki's plot, actually it just gives you a response of imaginary versus real, and the unit is basically at ohm centimeter square. This is also the same thing, ohm centimeter square. Okay, so when you look at the data, you cannot tell. For example, at half of this measurement, which frequency does your RCT finish? You cannot tell. You can only see it using border plot. Because from the border plot, then only you know at which frequency does the resistance charge transfer, resistance or solution start to form. Okay. In border plot, it is actually a combination of two plot together. You have one is actually modulus z. Remember back that I told you earlier, modulus z is actually a sum of imaginary plus with real versus frequency. If you see like some like this, W, this is actually known to be frequency. The function for both is actually in log. Log, both is actually in log. We'll get an information like this. As I told you earlier that to indicate what will be the electrical component that you will have in your system, you see how many flat line that you have. Over here, I have one and I have two. Okay. All right. So Fmax is actually here. So this indicates that Fmax is basically a turning point between low frequency and also high frequency. Okay, so this the region where the inner Helmholtz plane region, and this actually at the outer Helmholtz plane region. So the first flat line is actually equals to your RCT value, resistance or charge transfer. And the other flat lines at the higher frequency, this is actually your RS value, resistance of solution. Another plot is basically phase angle versus frequency. You get like a peak like this. The optimum point over here is basically known to be max. And if you have like one slope, okay, one slope, or one peak, this actually tells you that you have one capacity. So at the end, you already put in your mind, I have like two flat lines, so I have like two resistor, okay, two resistor and one capacitor. So capacitor will be the capacitor AA, okay. And I forgot to tell you that if you have a semicircle for your Niki's plot, this actually means that your circuit design is basically parallel. If Niki's plot is semicircle. When you remember back, simple Rendel's design between working electrode to reference electrode. Oops. This part is actually known to be parallel. Okay. So if you notice that your Niki's plot actually forming a semicircle, then you know that in your Rendel's circuit design, you have a parallel design. If you have like two semicircles, then means that you have two parallel. That is more complicated circuit design. But over here, okay, RCT from here is actually coming from here. RS is actually coming from here. CDL is actually coming from here. So with this plot, border plot and also Niki's plot, it gives some information what will be the prediction of your equivalent circuit, which later on you will use it for fitting with data. And once you fit, you will get the value RCT as CDL, a precise value. Okay. Fitting is also important because you cannot actually read the values manually because it all need calculation. You need a formula and whatsoever. So if you actually fit it with a model like this, okay, and the software will do it for you, and it will give you a more precise value, which you can use it in order to calculate inhibition efficiency, in order to explain about the process and whatsoever. Okay. I guess maybe I just end up with this one. Yeah, probably on the circuit, electrical circuit elements, we will continue on Thursday, because this is actually what I have like explained to you just now, how you actually can indicate the types of electrical models that you will use for your fitting. Okay. As if for now, is there any questions so far? Ada soalan? Anything? Samira macam mana? Okay. Dia nak tanya ke?
Ya doktor, saya nak tanya.
Ya, silakan.
Berdasarkan yang border plot tu,
Ya.
doktor beritahu tadi kata 2 flat line, 2 resistor. So yang satu slope merujuk pada satu kapasitor, betul?
Betul.
Okay. Saya nak confirmkan yang tu saja.
Okay. All right. Okay, I just maybe this one we will see on Thursday, but just want to have some teaser lah what you will actually see. Imagine that you have this kind of data. You have like border plot. This one is actually one border plot. Border plot one, you have like model set versus frequency. Okay. If you notice over here, the flat line is actually here, right? Isn't it? You have a one flat line over here. Other one is actually not showing anything. It's just one slope. Okay. So one slope actually tells you have one capacitor. Okay. And one flat line actually tells you have one resistor. In fact, for the phase angle plot, you have like almost half peak. So which actually tells you maybe you have like one capacitor. Niki's plot, it didn't form any semicircle. It's just formed a vertical line like this. Okay, so vertical line actually tells you the circuit design will be in series with the all information provided over here. Okay, from here, I know that, okay, I have like one resistor, and one slope, actually, I have like one capacitor. This also tell the same thing. I have one capacitor. And for Niki's plot, you have a vertical line, which is not semicircle. Okay, so with this kind of things, I already know, okay, one resistor, one capacitor, okay, one resistor, one capacitor, and it is a vertical line, so I have a series design, side by side, not a parallel design. Okay. So what would be like this one? So this one is actually, you see the plot, Niki's plot actually forming a semicircle. And it didn't have any resistance solution. Why? No RS, because the point is actually start from origin. So you only have like one resistor, okay, and one capacitance, maybe because of, like, we cannot see capacitance from Niki's plot, okay. But yeah, this one. From this border plot, you see that I have one resistor, one flat line, and one gradient, or half a peak, which actually indicate that you have one capacitor. The Niki's plot actually forming a parallel, semicircle. So when you have a semicircle, you know that it will be a parallel design. So one resistor, one capacitor. So this is actually the design, capacitor, okay, and parallel design because of the semicircle. So over here, as I said, there's no RS, resistance solution over here. Why? Because the value actually starts from origin, okay, immediately from origin. So you don't have any solution of resistance, okay. So that's actually the indication, and this is actually the one that we have discussed just now. When you have like a two flat line over here, one and two resistor, okay. Slope, I have like one slope and also one peak, one capacitor. And the design is actually, for Niki's plot, is parallel. So that is why over here, I will put a parallel design over here. Okay, and this actually have RS because it starts not from the origin. Okay? It starts somewhere after that, and this actually RS. The diameter is actually equals to RCT. Okay, so many things, I think, very but we will actually understand this more details, I guess, on our next lecture on Thursday. But at least you can get the point, right? You can actually know, okay, for EIS data, I will get this one. So in order for me to fit the data with a model, I should propose a model first. So how to propose a model? I should actually indicate what will be the component, how much capacitor, how much resistor that I should have. So looking at the border plot and also looking at border plot and also the Niki's plot, I can actually indicate, okay, whether this circuit is a series RC or a parallel RC or a random circuit model or what. Okay. All right. Any other questions so far? If you, I mean, if you feel like a bit heavy today, I cannot like, I just say that, okay, for EIS, of course, it is actually our expectation is a bit, the theory part is a bit difficult to understand because it's actually a combination of physics and also electrical which is not really our cup of tea. But just at least with this kind of explanation, I hope that you understand what's the purpose of understanding the circuit design. Because as I said, once you get the data, you need to feed the data with a model so that you get the value. If you want to get the value without fitting, you cannot actually read the value manually, because it's all a mathematical expression. You still need to calculate it. The best is actually to feed it with a model, then only you can get the data. So how actually to feed a model? You have to understand what will be the electrical component that you should have in your interface mechanism. So looking at the border plot and also Niki's plot, it can give you some prediction. What will be the circuit component, what will be the electrical component that you have in the circuit design. And from there, based on your hypothesis, you can actually propose a model and try to fit with this model. Okay? And the fitting is actually done by the computer, not you actually design the circuit and you calculate it. No. Okay. Any question maybe from the floor before we join the class today? All right. So if not, perhaps on assignment or what? Yes or no? Any problem with the assignment? Okay. So if no question, then I believe I will adjourn the class or the lecture of today. So thank you very much for your kind attention. Please don't forget to submit your assignment too. And I shall see you next Thursday. Okay, next Thursday. We are going to have a quiz later on. And with that, thank you very much. Wish you all the best in today. And Assalamualaikum warahmatullahi wabarakatuh.
Thank you so much, Doctor.
Thank you, Doctor.
Welcome.
Yeah, thank you, Doctor.
Welcome.